and I know in 112 Greg. So I started grading them, and so far it looks like people are really doing well, particularly on the part they usually do poorly on, the confounder and the causal link page. That first page, people are doing really, really well. So I'm very happy about that. That's always something that hangs people up. And so I'm really happy about that. So what we're going to do is we'll have your scores. We're going to grade all night till it takes us to, as long as it takes us to finish. We will post your scores tonight. And I'll send you an email so you don't have to keep looking. It's going to be late. I mean, we don't usually post the scores until about midnight. But I'll send you an email so you'll know when. And if you want to see, then I'm going to bring all your exams on Tuesday to class, no matter which section you're in. But if you want to see your exam before that, let's say you see it, you get a grade and you think, how did I do that poorly? I couldn't have. And you think it might have been misgraded, or you're worried and you don't want to spend all weekend worrying about it. Just come on Friday between 3 to 6 and we'll go over your exam with you and show it to you. Okay? So, all right. Now, so day after exam, it's sparsely populated, which is my very favorite time to do iClicker points. So I will definitely do it whenever I see low attendance. It's always an iClicker day. So get out your iClickers, we'll do it. And always it's more of a participation easy one. It's to give credit for those of you after an exam who came here. I know it was hard to wake up and come here. So I always do that. So. Okay, we're not going to do it yet, but just know that we are so you can get prepared. So, we are starting a new section on correlation. So, remember what we've just finished. The section we just finished was looking at descriptive summary statistics like the average, the standard deviation, the graphical summary histogram of one variable, just one variable. What do I mean by that? I mean for anything that varies. For example, our survey questions. How much do you weigh? That varies from person to person. And so we had 1,100 data points. Each and every person answered that question. And we summarized them with an average, and are you okay? You good? Is he in the wrong class or something?
No, he's in the right class.
Okay. You'll have to tell us the backstory on that one, okay? Sometime. Now, so we have these summary statistics. And instead of looking at all 1,100 people's weights, we made a histogram to make sense of it, and we average and standard deviation. Okay, so what's this section about? We're going to continue with descriptive statistics, but now we're going to look at bivariate data, two variables, and how they relate. Two variables. So the relevant pictorial display will be a scatter plot. And we'll still look at the average and the standard deviation of both variables. For example, let's say we wanted to relate weight and height. Okay, so far we've looked at them separately. Now what we're going to do is see how they relate to each other. Do people who are taller, do they weigh more? How do they, so we're going to show that on a scatter plot. And the degree, the strength of that linear association, the strength of the linear association is going to be measured by something called the correlation coefficient. So things like, for height and weight, the taller you are generally, the more people weigh. So that would be a positive correlation. About like exam scores, the better you do on exam 1, do you think the better you're going to do on exam 2 as well? Do you think people who score really high on exam 1 are also going to score really high on exam 2? And people who really bomb exam 1, don't you think they're more likely to bomb exam 2? Yeah? So that would be another positive correlation. So the first thing you do, let's just get started, make sure everybody knows how to do a scatter plot. And so that's what this section, this next section is about. Part 3 is all about correlation and linear regression. He's back? Is that you? Okay, now you gotta tell us what's going on, because I'm so curious. Go ahead. What happened? Oh, is the eye clicker? You had to run and get it? Was that it? Oh my goodness. And you're so excited about it. You just shout out, eye clicker, and run out the door. Ah, such enthusiasm. Okay. Now, all right, so let's begin. So what do we do here? We have 2 sets, just a real simple example. Pretend you have these students, 1, 2, 3, 4, 5, 6, 7 students. And here's their exam score. So the first one got a 55 on exam 1 and a 62 on exam 2. Not a very good student. So here's 55, that's what he did. This is exam 1 on this axis. Now how do we decide which axis to put these 2 variables on? Well, usually the convention is to call the X variable, in this case we're calling it exam 1, the independent variable, and the Y variable the dependent variable. Because usually you think, okay, the independent variable somehow is thought to influence the dependent variable. Why did I put exam 1 on first? Because exam 1 on the X, because exam 1 came first in time. How about with height and weight? Which do you think would influence? Which do you think would be the independent variable? Height or weight? Do you think height? Yeah, why do you think height? You're right. Why would you put height on the X? Right, the taller you get, the more you weigh. If you gained a whole bunch of weight, are you going to necessarily get taller? No, you're not. That would be good, huh? No. So that's why the height influences. Good, so you understand this. Now, so let's map these out. So the first one was what? 55 and then 62, so that's that point. The next one would be 60 on the X, and then we go up. Oh, we don't go up at all. That person didn't do very well. On the second one, that's 50. Then the next one is 70, and we're going to 65 right there. And 80, 70 is right here. 85, all the way up to 95. 90, 80 is there. And the last person got 100, but not 100 on the second one. Instead, he got 90 on the second. So that's what our plot looks like, the scatter plot. And if there's a positive association between X and Y, then the pattern of the points slopes up. See how it slopes up? The people who do above average in both are way up here, below average in both are like that. So this one, do you see there's a positive association? If there's a negative association, then it would slope down. It would slope down. That would be weird. It would be the people who, what would that mean if it was sloping down? So the people who would start up here, so those are the people who did what? Terrible, flunked exam 1, but ended up getting hundreds on exam 2, really what? And then it would be all the way, it would look like this. So the people who did extraordinarily well on exam 1 would bomb exam 2. Do you think that's very likely? No, that would be unusual for this set of data. For other things, it would be likely. Okay, so there's a negative association when it slopes down. So is there a positive or negative on the exam 1 and exam 2 above? We just said there's positive because it slopes up. All right, so just using common sense, do you think that there's a we could do these as eye clickers if you want, or we could wait. Well, why don't we wait? Okay, so for following pairs of variables, state whether you think the association is positive, negative, or neither. For height and weight, what do you think? Positive. The taller you are, the more you generally weigh. So that's going to be positive. How about this one? The weight of a car, the heavier the car is, and how many miles per gallon it gets. Negative, right. Negative. Why? Because the heavier the car, the worse gas mileage it gets, right? If you have a big SUV, it doesn't get very good mileage. Okay, how about the next one? Years of education and income. The more you go to school, the more money you think you make on the average, or the less? Positive. You hope, especially you're here, right? Sitting here through college, you hope it's going to increase your income. Okay, so that's positive. It is. How about this one? The height in GPA among college students. What do you think? Negative, positive, or neither? Yeah. Do you think from knowing how tall somebody is, looking at them, you'd have any clue what their GPA is? You wouldn't. So that's, what should I say here? Neither. How about something like height and ability to read, reading scores among all grade school kids? If you saw a grade school kid and you saw they were taller, I mean, I'm talking about through all the grades, do you think, we wouldn't look at a particular grade, but you take all the kids together, and do you think the taller kids can read better? Yeah, because they're probably fifth graders, and the shorter kids are kindergarten kids and can't read so well. But do you think it's the height that's helping them read? No, so the confounder there would be what? What would the confounder be? It looks like, you know, the taller kids can read better, so we see this association, but we know that's just an association, it's not causal. And in this case, the confounder would be clear. What would it be? Age, exactly. It's age. The older kids can read better, and the older kids are taller. Great. Okay, so now how about this? Temperature in Fahrenheit and temperature in Celsius. Now think about this. As one goes up, does the other one go up? If that's the case, then it's positive. Doesn't matter that one's always, do you think it's positive or negative? As it gets higher in one, doesn't it get higher in the other? Doesn't it? So it's positive. I know there was some hesitation because you know that one number is always lower than the other, but you know, think about it, one number is always higher. If one it's how they're related. As it gets to be a higher temperature in Celsius, it's a higher temperature in Fahrenheit and vice versa. Okay, how about the number right and the number wrong on a test? Negative. Because the more you get right, if you got 100, would you get any wrong? If you got them all right, you wouldn't get. So the more you get right, the fewer you get wrong. So that's definitely going to be negative. Does everybody understand that? All right, so let's turn the page. Now, okay, so this correlation coefficient, this association that we're talking about, measures the strength of a linear association between the two variables. It measures how closely the points hug a line. It does not measure clustering around a curve. It can be deceptive if it measures if you have a curvilinear relationship. So why would it be deceptive? Because, for example, if you have, if you have something like this, here's X and here's Y, and you're looking at, let's say it was a curvilinear relationship like this, like here you'd get a negative relationship, and here you'd get a positive relationship. And you know what R would do? If you used R as a measure of correlation, it wouldn't be able to distinguish between this and a situation just completely, it wouldn't detect any pattern, because it would say, oh, here's the negative, here's the positive, and they'd cancel out, and it wouldn't be able to tell the difference. If you just, the measure of R for both of these would be 0, no relationship. And clearly there's a relationship here. So it does, basically the correlation coefficient goes between -1 and 1. If all the points, if they're perfectly correlated, if every single point lies on a line, a perfect line like this, that's a perfect 1. You can perfectly predict 1, given the x, you can perfectly predict the y. Or -1 would just look the exact opposite. You can't get higher than that. And you can't get lower than if you had no relationship at all, none. Knowing x told you nothing. Like if this was people's height and this was GPA, height and GPA, knowing their height tells you nothing. They could be really short and doesn't tell you anything. Their GPAs range all over the place. They could be really tall and their GPAs range all over the place. So it looked like this. It has just totally random. So that would be R equals 0. Where if, let's say, perfect prediction would be, let's say, what would be a perfect prediction, a perfect correlation? Well, you'll think about that for a while, but if there is one, there'd be a formula, and you'd know exactly, if I told you what x was, you'd know exactly what y was. Just a linear formula. Okay, so now, is R an appropriate summary statistic for the plots below? Why or why not? Well, which one, do you think it's appropriate for this one? Yes. In this case, R, they just would equal 1. How about for this one? Do you think it would be appropriate? I mean, they're all over the place. There's no pattern. Would the correlation coefficient correctly tell you there was no pattern? Here. Yeah, I think it would. It would say R equals 0 because there's no pattern. It would say R equals 0, so it would be appropriate because there really is no pattern. As opposed to this one, this would be no. You know why? Because R would say R equals 0, but there is a pattern. When you hear R equals 0, you think, oh, there's no relationship between the variables, like height and GPA. There is a clear relationship between the variables here. Like, let's say this was, dosage on a medicine, so that there's an ideal dosage right here. So here, if you take too little, this could be a medicine, and this could be how well it works, the cure rate or something. And if you take too little, it doesn't work. If you take too much, it doesn't work. There's like a happy medium. So there is a pattern. Whereas here, if it was a medicine, the same thing, and you wouldn't even know how much to prescribe. There's just no relationship at all between how much medicine to prescribe. Yeah.
So why is that no and that one is?
Because what did the question say? They're both, why is that no? This is R appropriate? Because R says to you, it's inappropriate. No, we don't want to use R here. Because I would tell you this medicine just doesn't work. It has nothing to do with it. It clearly does. I don't want to use R. What I want to use is some other variable, not R. Good question. Either I could do two things. I could split it maybe in half and do two separate graphs, and then R would be positive here, and then R would be negative there. Or I could do something, use a different measurement, transform the data somehow, but I don't want to just give R. Whereas here, wouldn't it be appropriate to just say, yeah, this medicine doesn't work because R zero has no relationship between the medicine and the dosage. Wouldn't that be appropriate to say? Yes, so R accurately tells you there's no pattern. R accurately tells you there's, good question, no pattern. But here, there is a pattern, so R inaccurately tells you there's no pattern. Do you understand? So here, R accurately tells you there's no pattern, and here, R tells you there's no pattern, but there really is. So don't use R. Use R for curves. You see, this is a clear curve. You can use R when there's just scatter like that. Do you understand the difference now? Okay. Here, I don't have time, place to, R is equal to 0. But there is a pattern, so R is wrong here. Don't use R if there's a curvy linear relationship. All right, how about here? Do you think R tells you how closely, like here, this would be appropriate because R would tell you, we'd get a positive R, and it would tell you that the points slope up. So you basically, what did I say here? It's relevant when the scatter plot forms like an elliptical or football-shaped cloud, like this. Or when it's a straight line or scatter, but it's not for something like this. How about this one? Well, there's two football-shaped clouds. There's one here, and there's one here. Now this is kind of, this is, we'll get into this more later, but you know what, if we just took an overall correlation of this, you know what do you think there's a positive or a negative correlation here? What do you think? It's hard to say. Well, some of you are saying positive, some of you are saying negative. Depends on how you look at it. What if we did compute R, it would say positive, because it would see a big group up here and a big group of people down here, all these points, and it would say, okay, there's a positive relationship. But wouldn't that be deceptive? Because there's really two groups of people. There's really two groups of people. There's people down here that have a negative correlation, and there's people up here that also have or data points up here that also have a negative correlation. There's two separate groups that are both negative. I should have pulled up a good example of this. Let me think of a good example. I have a good example where it's sort of like this. Here's a good example where it's, let me think. So let's say this was height and this was weight, okay? And let's say there's a group here that are short, but weigh a lot. But the taller they are within this, they weigh more. And then there's a group here. Now, R would say there's a negative correlation, but there's really two separate positive ones. And this could be like sumo wrestlers who weigh a whole lot. They weigh a whole lot, but they're short. So if we look at just the sumo wrestlers, there'd be a positive relationship. And these could be like basketball players who are much taller, they weigh less, and there's still a positive relationship. But when you overall, if you did R, it would say there's a negative relationship. So it's confusing. So you don't want, if you see two separate groups like this, then R is not appropriate. So no, you'd want to split the graph. Okay, do you understand? So you'd say no, because R would inappropriately, is that the right, how do you spell it? Inappropriately. Sorry, that's spelled so badly, looks so badly. Inappropriately give you what? Positive, when there's correlation. When there's really two groups of negative. When there's really, so you'd want to break the data down. Boy, I can't fit it in. You really have two negative groups. Thank you. And you really have two negative groups. You know, this is really a remarkable class for such a big class, because I never usually, and it's helping me a lot, because I never usually get feedback like that while I'm talking in these big lectures. So I just have write these little notes and nobody says anything. And I don't have to, now I'm going to have to expand my notebook. So Jonathan, I really appreciate your questions in particular. Thank you. Okay. So now, if you can read this, it says the correlation coefficient is between -1 and 1. All right? And the closer the points hug a line, the closer they do, the closer it gets to a perfect correlation. And if there's no association, then it's basic, the correlation 0, and it looks like this. Just knowing this tells you, like knowing if this was height and this was GPA, knowing your height would tell me nothing about your GPA. There's just complete scatter. All right, so now let's see. Here's some examples of correlations that are perfect. It means you can perfectly predict one variable from another. So if I knew somebody's age and date of birth, if you know somebody's date of birth, you know exactly what their age is, right? And vice versa. Height in inches and height in centimeters. If you tell me your height in inches, then all you have to do is multiply by 2.54 centimeters per inch, and you know exactly what the height is in centimeters. There's a formula relating the two. Does that make sense to everybody? All right. So now, and then here's a correlation of 0 means like weight in ACT. If I looked at you and saw how heavy you were, would I have any clue about your ACT score? None. And how about like attendance in Stat 100 and the number of pets you own? I can look at your attendance and I would have no idea how many pets you have from that. All right, so like on the previous page, let's see if any of those were 1 or -1 or 0, or if they were in between. So let's look back. Were any of these perfect correlations? Any of these positive or negatives that we see up there, are they a perfect correlation? If I told you one and you had the formula, you'd know the other. Yes? Exactly. Temperature, if you have the formula, you can convert temperature in Fahrenheit to temperature in Celsius and vice versa perfectly. So this is a perfect correlation. Doesn't everybody agree? So that is a perfect positive correlation. That means if you looked at the scatter plot, what would it look like? You'd know it was what? A straight line. Every single point would be on that straight line. Do you understand? No point would be off it. Is there any other that's perfect? Yeah.
The next one? Right versus
yeah, and the number of right and wrong on a test. Let's think about it. That's true. It's perfect negative. Why? Pretend there were just 10 questions on the test. Okay, let's think about it. What would the graph look like? If there were just 10 questions, and here's what I'm doing. And here's, so it would go from 0 to 10, and 0 to 10, and here we could say right, the number right, sorry, and here would be the number wrong. Now, let's say I told you you got 0 right. How many wrong did you get? 10. So you'd be right up here. What if I said you got 10 right? How many wrong did you get? There are only 10 questions. If you got 10 right, you got how many wrong? 0. So it would be this line. 5, 5 would be right here. If you got 5 right, you'd know you get 5 wrong, 1, 9, etc. They'd have to add to 10. The equation would be wrong plus right equals 10. That's your equation. It's a linear equation. So you'd know perfectly. Do you understand? Okay. So that doesn't happen except when you have a formula. Otherwise, you're going to have correlation coefficients that are somewhere in between. In actual data that we collect, like let's say you took the heights of identical twins. Wouldn't you think if you knew the height of one twin, you'd know the height of the other twin, and there'd be a correlation of exactly 1? Would you think that? It's actually not exactly 1. Like in any real world data, it's not, because they're not exactly the same size. If you know twins, there's usually a little bit of a difference. So in any real data that you actually collect, you're never going to see those type of perfect correlations. I think it's 0.95 or something, the correlation. It's very close to 1 between the height of identical twins. All right, so now let's go back and see where we're at. Okay, so now we're on page 81. All right, so basically, you can summarize the statistics of plots that have sort of what I call, the book that I was using called a football shape. If you can sort of like detect an elliptical pattern like this or a straight line, you can summarize them with 5 summary statistics. All right? And what are they? Well, here's 4 of them. The average of the x, the average of the y, that's 2, and the standard deviation of the x and the standard deviation of the y. Those are 4 of them. And you know what they tell you? The above, these are 4 summary statistics. Ones that we've already learned. Those are the 4 summary stats we already have. But you know what these 4 tell you? If you're drawing a scatter plot, of x and y, you know what they tell you? They tell you, this one, the average of x and y, tells you the exact center of the cloud. The exact center. That's the average of the x and the average of the y. That's what this one tells you. And for all these plots, all 8 plots here, the average of the x and the average of the y is the same. I drew them that way on a computer. I made the averages the same. Okay? So that's what you know with this one. This tells you the center of the cloud. Do you see? And they all have the same center. They don't look the same, but they do all have the same point of averages there. Now, what does the standard deviation of x and y tell you? Well, the standard deviation of x measures the spread. X is this way, and the standard deviation measures the spread. So the standard deviation of x measures the horizontal spread of the cloud. Now let's look. So basically, it measures this spread. Let's look at them all. You see, spread from here to along here. You see, from the lowest to is the range, but the scatter is really the same. They all have the same, even this one. If you laid the points, how can you see it? If you laid like this point on its side, they all have, they're kind of bunched around the middle, and they're all spread out in the x-axis the same way. Same down here. Every single one of these plots has the same horizontal spread. They also have the same vertical spread. I drew them that way, so that the standard deviations of the x and y's are the same. You know how you can think of it? What that tells you is that the box the cloud is in is all the same size, because it's the same this way and the same this way. Pretty much the box and is pretty much the same. And they're spread, the points, there's more points in the center here. So let's write this down. So all 8 plots have the same center, the same average for x, the middle, average for y, standard deviation for x, and standard deviation for y. I drew them that way. They all have the same. But do they look anything alike, those scatter plots? What's different about them? What's the one statistic that's really different about them? What do you think? The R value. That's what's really different. R is different. And that's why you need 5 summary statistics to describe 2 variables. You don't only need their averages and their standard deviations, but you also need their R, and then that describes the pattern. So that's what I say here. The above statistics, these 4 statistics, tell us the size and location of the box the cloud is in, but nothing about what the shape of this cloud is. They don't tell us anything about the relationship between X and Y. Those statistics, these average and standard deviations, it would be like we could have side-by-side plots. You know? We could even have, side-by-side, but they don't tell us how they're related. Imagine if you had 2 side-by-side histograms. One over here is height, and one over here is weight. But you have no idea how they pair up. Well, then you couldn't get R. For R, you need a scatter plot that relates the 2 of them and a measure of their association. Okay? So they each had 100 points, and the average and standard deviations are the same, but the plot correlations are different. Okay? But R is different. They have different shapes. Okay, so now let's look at how R is measured here. So this one, this is R equals 0. Can you see how there's no relationship here, pretty much? Like knowing X doesn't really tell you anything about Y. Because if X, if you're down here, there's a lot of spread. Can you see that this has a little bit of a positive correlation? Can you detect a little uphill here? Maybe it's hard can you see that? This slopes uphill a little bit, and this uphill a lot more. It's clustered more, and this is really close, 0.99. Now, those are all positive. Let's look at the negative ones. This one, can you see it goes down negative a little bit? It's kind of a lot of scatter. It's not perfect by any means. There's a lot of random variation, but it does slope down. This more so, and this one's almost a perfect. Okay? So let's do, why don't we just do this one online? We can just, we'll do this one here, and then we'll get out our iClickers, and I'll give you some online. Okay, so let's look at this one here. And let's see if we can match them up, and then we'll do the same thing online. So what does this even say? I can't see it. Negative 0.68. So you have to match the correlation coefficients to the plots. Which one do you think this should be? Negative 0.68. Which one, first of all, which one slopes down? Let's do this one first. This one's easiest. Which one's this one? That's 0.88, right? It's going up, so that's B. Does everybody see that? Okay. Is there any others that slope up? This one? Would you call that sloping up? Yes. So that has to be, that has to be right here, right? Now, that slopes up. Now we have these 2. Which one, do you see how this one's stronger? Isn't this a stronger correlation? So this, we have 2 choices left. Should it be this one? Negative 0.68. That's closer to -1. That's a higher absolute value. So that has to be C. Do you see that? And this one's just a slight downhill. That's going to be closer to 0, a lower absolute value. So that has to be this one, doesn't it? Does that make sense to everybody? Does that make sense? All right, let's do it on the iClicker. Now we'll do some examples like this. So let's go to the overhead. This is really hard to tell between negative 0.57 and negative. Let's just see if you can do it without the iClickers. I can't, we couldn't possibly do this, right? How do you know? I mean, between these 2. Should we try it? Okay, so what do you want me to, let's do the ones that are pretty easy. Let's do this one first. Which one's this? B, and then this one's going to be the other positive one, which would be what? D. Okay, now we've got these 2. This one's supposed to hug a line more. Is it going to be A or C? C? You shout out C if you want C here. C. Okay, so then the last one has to be A. All right, let's see if we get this right. Is that right? Yeah, 4 correct. It should turn green. Yeah. Okay, now you're ready. Let's get new plots. That's not a good one. One I would put on your exam. Let's get some new plots. How about this one? This one we can do. Okay, get out your eye clickers. I think you can do this one. All right. Let's start with this. Negative, whoops, let's start the eye clicker here. Got to move it down here. All right, so we're starting with this one. Negative 0.88. So is it this plot, negative point, this one, or this one? Okay, you just click on your eye, do it on the eye clicker. This is for points. What? The other one, we're doing this one. So which one do you want negative 0.88 to be? A, B, C, or D? Vote. Okay, so y'all voted. Let's stop it. And now, what did you choose? D. Okay, let's see. That is correct. And let's look at how many people chose it. Great. Okay, good. Let's do our next one. I'll start this going. And we're doing this one. 0.21. 0.21. A slight. Which one is that? 0.21. Well, we know it's not D. We've already answered that one. It's the lowest, yeah, it's the one that has that looks most random, I guess. Okay, so we'll stop it. I'm curious how people did on this. Okay, so I think I would have chosen B. Is that what you would have chosen? B. Oh, you chose. I think this one has more of a little pattern. This is a hard one. Okay, so let's see what you guys did. You chose A. Am I wrong? All right. Well, we'll go with A, and we'll see what happens when we have to. Won't give us our answers until we're done here. Okay. So let's do the next one. Okay. So we're starting the next one. Oh, but wait a minute. What if you want B now? You know, don't assume it's A. This is terrible. These are all tied together. Everybody's going to get participation points. Just see what you think on these. Because I mean, if just see what you think between these. I thought this one would be A, but I could be completely wrong. On the exam, I'm not going to give you ones that I'm going to give you ones that are more clear. Yeah, like in your notebook. But let's just try it. I think A looks more like a stronger uphill. I would have put A for point, but who knows? Let's see what you guys say. Okay, I'm stopping it. Let's see what you guys wrote. So now you have B for this one. All right. I really want to do the other one, but we'll go with you. I'd really like to do that, but all right. Well, this one has to be what? This one has to be C. So let's see who's right. Oh, sorry. Sorry, I shouldn't get happy about that. Only been teaching this for how many years, and I got it right. Okay, but you're wrong. Okay, so you got, it should have been what? This and this. It's hard to tell. The reason why I thought it was like this was I felt like these extremes. I saw more of an uphill. Like this looked more random. Do you see what I mean? I'm not going to give you that one on the exam. You all get credit on that eye clicker. Okay, this, I'll show you like how would I do it. Would this be a fair exam one? I think this would be a fair exam one. Like This one would be which? Negative 7.4. There's only two negative ones. And do you see which one? There's two negative ones. Which one's stronger, higher? Which one should this one be? A, yes. Then our other negative one would be what? C. Does everybody see that? This is how an exam question could be. All right, now we've got two positive ones. These are easy. Which one's this? It's D. It's just all random. And this one's almost a line. This would be a perfect exam question. Yes, and our answers, hooray, we are right. With a 62.5, not bad, right? Okay, so now let's go back to the overhead, and we've got some other stuff to do. Okay, so we did all that. Now, all right, so we've been talking about this line. We've been talking about this line that the points, if there's a perfect correlation, all the points hug some line. You know what that line is? This is going to relate back to our z-scores. You know what that line is? That's the line if I turn both variables into z-scores. Imagine this. Turn both variables into z-scores. If there was a perfect correlation, each and every data point would have the same z-score for x and y. So for example, if there was a perfect correlation between height and weight, if I changed all of your z-scores for height and your z-scores for weight, you'd all match up. The person who had a z-score of 1 in height would also have a z-score of 1 in weight. It would be like a person who had a z-score of -3 in height would also have a z-score of -3 in weight. That's what it would mean. Think about it. Height is in inches, weight is in pounds. You need a common measuring stick. A common that not only measures your ranking, like the very tallest person would also have to be the very heaviest person, but also measures how extreme you are, your distance from the average, the spacings between. For example, in two races, you know, it wouldn't only if two races had, let's say one was a bike race and the other was a swimming race or something. And your times, if there's a perfect correlation, it wouldn't only mean the fastest person in one was also the fastest person in the other, and the ranking was the same. The second person in one was the second person in the other, and all the places were the same. It wouldn't only mean that. It would mean how phenomenal the first person was on one race would have to be exactly the same degree of phenomenality, what's the word, how amazing that person was in the other race. I mean, that you'd have to be that distance from the average. Because the z-scores not only give you a ranking, but also a spacing. So everything would have to perfectly match up. And z-scores tell you that. Z-scores tell you how many standard deviations you are from the average, and it's a common measuring stick. So this is the ideal. If you have a correlation of 1, it means your z-scores in one variable perfectly match up with your z-scores in another. Like if there are two sets of exams, your exams and the final, it wouldn't mean you got the same score. It wouldn't necessarily mean you got, a 90 on one exam means a 90 on the other, because it could mean something completely different. Like a 90 on exam 1 isn't as good as a 90 on the final. People on the final do much worse. Not much, but somewhat. 90 on the final is a much better score relative to the rest of the class. So it means you'd have the same z-scores. All right, so that's the idea. So what is this? So that's what I say here. The correlation coefficient measures the strength of association between x and y by measuring it closely. It hugs a line. What line? Well, it's called the SD line, the line that says the z-scores are the same. Your zx is equal to your zy. It's that line. Once you change, see, not the x equals y line, but the zx equals zy line. All right? And the slope of it is if the slope of the z is 1, if you go over 1, it's, slope is rise over run. So if you start at, I'll explain this in a minute. Let's just think how to graph it, okay? So here we have some data from, this is real data from a former Stat 100 class. And there's scatter. There's a positive correlation between students' average exams, and this is the average on the exams was 83. This wasn't when I was teaching. My scores are better usually. Okay, the average was an 83, and the final was 74. And here's the standard deviations. So, this line, and there's a positive correlation, and this SD line that I'm talking about isn't going to be x equals y line, because look, the averages are different. An 83 on one exam is not the same as an 83 on the other, or anything like that. But so it's the z-scores would be the same. So how would we even think about that? How would we draw this line? So start at the average. Okay, what is the average? The person who is average in both, has a z-score of 0 in both, is going to be on the SD line. Now, let's think about it. So that's 83 on exam 1. So that's about right here. About 83, that's going to be z equals 0. And if he's going to be on the SD line, he's also has to have a z equals 0, not an 83, but an average score in the final. So z equals 0 in the final is a 74, not an 83. So we go to here's 70, right? And 74 would be where? I'm sorry, the scales, I got to do a better data program. This is 70, so 74 would be about right here, right? And that would be z equals 0 for y. Okay, so where is that? I would say that's this person right here. There is somebody who is exactly average on both. Exactly average on both. All right, so that person has z equals 0 in both, but in 83, 74, but 0, 0 in z-scores. Agreed. Now, 2 points determine a line, so why don't we just look at the person who has 1, 1 in z-scores. That person will also be on the line. The standard deviation line. The line is if you did exactly the same in both exams. That's the line. So let's look at somebody who has a 1, 1. What would that mean? A 1, what does a 1 mean? It means 1 above average. 1 what above average? Not 1 point, not 84, but 1 what? One of these, 1 standard deviation above average. So a z-score for the x's would be what? 83 plus 9. Do you follow? So it would be 92, wouldn't it? 92. Let's look at where that is. So right here at 92 is z equals 1 for x. Now, if he did exactly the same on the final, he wouldn't be getting, he wouldn't get, what did we say this was? A 92? He wouldn't get a 92 in the final if he did exactly the same in terms of z-scores. What would he have? Not a 92, but what? He'd have 74 plus 1 of those. Do you see what I'm saying? Doing exactly the same would be 1 above average, 1 standard deviation above average. So he would get an 84, which would be right 74. Here's 90. So 84 would be about right there. 84. And that's going to be a z equals what? zy equals 1. And this is a 92, and this is an 83. So let's graph that person who has a z-score of 1, 1. That would be 84 is right here. Isn't that true? You see? Okay, so that's 84 is right there. These are all the people who did, they all got 84s. They all had a z-scores of 1. But where's the person who also had an x? Okay, so he had a z-score of 1 with x too. That person right there. Is that right? Does that look right to you? No. Did I do that right? My eyes are so bad. Did I match it up right? Let me see. Yeah. Why didn't you, what was I doing? Oh, look what I did. I did the 70, not the 74. I am so sorry. You're so forgiving, but if it was an exam, I would take off, because she'll never learn otherwise. She'll never learn. You have to take off. Okay, so I did that all wrong. So that's an 80. Cross that out. That's the, thank you, whoever said that. Extra credit point, don't you think? For noticing that? Yeah, might as well. Okay, so this is an 80 there. I knew something was off. And now, how about this one? Am I right here? 84 and 92. Does that look right to everybody? Okay, so this is, now which is the X? Tell me, 92 and then 84. And tell me in z-scores, what am I supposed to write here? Please, help out. 1, 1. And this 2 points determine a line. So if I just connect these 2 points, I'm just going to connect these two, I am going to have a line that will have every single person on this line, everyone, oh, terrible down there, but the same z-scores in both. All these people, here's one, here's a few people that did exactly the same in both, and it's called the SD line. And if there was a perfect correlation, every single person would be on this. Every single person. You wouldn't even have to, after a while, you wouldn't even have to take the final. I'd know what the scores, I'd say, okay, you're going to get the same thing. Why even take the final? Not the same thing in terms of a number of how many were, but the same ranking. Okay, so this is the SD line, and another way to say it, what's wrong with this? Is it the X equals Y line? No, X is not equal to Y. It's not the X equals Y line. It's the ZX equals ZY line. All right? And so it means there's a slope of 1 standard deviation. So now let's go back over here for the slope, and maybe we can see what it means more. So if you go over from the average, 1 standard deviation in the X direction, which was 9, and you go up 1 standard deviation in the Y direction, which was 10, and they're not drawn to scale, which is why it's scrunched in. If you do that, that is 1 standard deviation in the X, and this is 1 standard deviation in the Y, and you're probably wondering, that's 9, that's 10, why is this shorter? Don't worry, it's just the graph got squished. Okay? That's rise over run. 1S, so let's write rise over run. Run. All right, so it's 1 SD, that's your rise, and that's your run. And that's where that comes from. And if it's negative, it would just be the opposite. It would be what? If you were 1 above average on your exam, you'd be below average. On the it would slope down. That would be weird for exams. Okay, let's turn the page. Now the last thing we have to do is, I think you're going to like this because it ties together what we did before. Okay? Now this is our real data where, didn't I give you this on the exam, except our data was slightly different. On the exam, the average girl was 135 pounds from our survey that we did this semester and what you had on the exam, and it was 24 was the standard deviation. So it varies slightly. This was another semester. And here's the height, okay? Now what I'm asking you for, you can see there's a positive association here. But this line right here is the SD line. And if every girl was exactly as heavy as she is tall, she'd be on this line. So for example, I say in the table below, the heights of 3 female students are given. How much would each have to weigh to fall on the SD line? In other words, if they were exactly the same heaviness relative to the rest of the class as they are tall, how heavy would they be? So just to picture it, let's just look at these girls who are 5'11", the first one. Where are they? They're these girls right here in this column. These are all girls who listed 5'11", right? Now, these right here, they are just exactly as tall as they are heavy. A lot of them aren't. A lot of them are lighter. But these up here are exactly as heavy, as they are tall. So what is that? We can look and see. It looks like about 180, but let's get it exactly. How would we get it exactly? Let's look. So what would we do? Well, this is in inches and this is in pounds. We have to go through the z-scores. We mean that they're the same in z-scores. So this is their z for height, and then it will be the same for weight if they're on the SD line. So let's get their z for height. How do we do that? Remember, it's the value minus the average over what? Oh, over the SD. So we want to say 71 inches minus what? We have to look up here. Minus what? Over what? Yeah, look where I'm pointing. 3, thank you. And what is that? 6 over 3 is 2. So this girl is 2 standard deviations above average in height. If she's exactly as heavy, what should this be? If she's exactly as heavy, if there was a perfect correlation, wouldn't she be 2 right there? That's what it means. But she wouldn't be 2 pounds. What is she? Let's start at the average. What is the average for weight? 135. Okay, so does this mean she's 2 pounds? I'm going to add 2. Does that mean she's 2 pounds, 137? Is that what this means? Is that what it means? What does it mean? It means she's 2 what? Standard deviations. So she's 2 times what? 25. Yeah, we're in pounds. So this is the standard deviation for pounds. So how heavy is that? 135 plus 50 is what? 185. So that right here, let's just mark it, is 71 inches and what? 185 pounds. But in z-scores, what is it? Tell me what it is. 2 at 2. She's right on that line. All right, let's look at the next set of girls. Let's look at the bottom one. There's 62 inches. So that's this column. This is 60, 61, 62. There's a lot of girls that are 62 inches. That's 5'2". Okay, so it's this column of girls right there. Okay? Now, this is the SD line. So these are the girls that are weigh just as little as they are short. So let's see what that is. How would we figure that out? So we'd say 62 minus 65 divided by what? 3. And what is that? -1. And then we're just going to say if it's the same, she'd be -1 here. So you'd say 135 minus, not 1 pound, but 1 what? 1 times the SD25, so that's 1, so that's 110. That's how little they weigh. So let's mark that in. So this right here are the girls who are 65'2" at 110 pounds. Or z-scores of -1, -1. Most of the girls are heavier than that. But there are some that are exactly there. Now let's look at the last one. The last one is what? An easy one. Can you see this one? 65. That's right at the average, so it's a z-score of what? Z-score of, come on, y'all know this. What's right in the middle? 0. So what the weight's going to be? 0. And what's the weight going to be? Average. This is exactly average. So this is this right there. And that is the point of averages, it's called. And it's 65 inches and 135 pounds. But in z-scores, what is it? 0, 0. This is the SD line. This other line here we're going to learn about later. It's called the regression line. But right now, this is the SD line, and that's what we're concentrating on. Now, you know what? Do people get this so far? All right. Now, let's turn the page, and I want to show you something. We were going to compute, we're not going to do this, but I need your advice. Okay, I need your advice. I don't know what to do here. All right, so probably some of you realized that you've looked at the homework, and I've already posted a problem on how to calculate the correlation coefficient. The problem with ln kappa, the course, the homework program we're in is, I can't like go back and say, no, you can't, don't do that. It will mess up your grades. So I'm trying to think of what to do. So probably, I'm going to try to figure out what to do. I mean, you're not going to have to do this problem on correlation coefficient, but we're going to have to figure out what I think I'll probably do is leave it up there on the homework, because otherwise it'll just mess up everybody's scores, like people who've already done it, the homework. I'll leave it there. You don't have to do it. If you want to try it, you can. I can post notes for it if you want to try it, but it won't count. It won't count. I'll just give 0 credit for it, and then I'll post another one for our next homework, and that one will count. Or the same one. I'll post the same one, and it will count for points. How's that sound? Does that sound good? All right, thanks. Goodbye. Have a good weekend. Hope you do well in the exam.